Hi and hello everyone. What we have been seeing is the general Markovian queues with different features. When you add, how the system gets complex. So, we are within the Markovian framework, we are looking at it. We have seen priority queues earlier. What we will see next is a feature which is also quite important with respect to many practical applications, especially in computer and communication systems, or in a network scenario, or in a mobile network situation, or even otherwise, even other places. This is a feature which is has lots of importance and needs to be tackled or need to be incorporated into our modeling framework. Okay, and this is called the retrial phenomena. Okay. So, what is this feature? This feature captures the phenomena of customers who make repeated attempts to access the service facility when they are not getting into the service at the first place and their immediate arrival time. Okay. A simple example could be a customer calling a local service center. Say you have something to be done and you want to get connected to that. For example, you have your car which needs to be serviced. So, you are calling the car service center there. Okay. So, what you do is you make a call, right, and at the first place you see that it is a busy tone, right. So, which means that you are not able to get connected to that service facility, right. So, what you do, okay, you hang up, you try again after some time. Okay. You may try immediately, that is also possibility, right, or but you know that when an ongoing call is there, so you might think that at least 1 or 2 minutes gap I will give and then I will make a call again, right. So, you make a call again after 2 minutes or 3 minutes or 5 minutes, again you might get a busy signal, or you are able to get a free, that the other side is there picking up the phone and then you can get the service. Second time when you get busy signal, what you would do? Okay, fine, then I will try after some time, like again you disconnect and then make call after some time, right. This you may do indefinitely, or after some time you will lose your patience and you say, okay, like I will try afterwards at a later point of time, right. So, this is everything is possible. So, this is the repeated attempts to gain service is what we call it as retrial, and the queues which has this feature is what the retrial queues. Okay. So, the basic idea we will depict like here now. Okay. So, what you have a service facility, right. So, you have a service facility here to which customers come. So, which we call it as primary customers come, and if they find the service facility free, or there is at least one server available to get their customers leave, right. It is a normal phenomena that you might have. Then when this particular case, if there is no service facility is busy, right. In that case, what might happen, that you would have what we call, this is orbit. So, the customers in orbit, they get into that, right. So, it could be the scenario that when the service facility is busy, they can get into orbit in this way, or they can leave. Okay. Leave, this is what we say as impatience also, right. So, this is a general depiction of the scenario that might happen. In this scenario, that you have a service facility to which the primary customers come or customers arrives, and if the service facility is free or if there is at least one server available, then they get their service and they leave. It is a normal phenomena. Now, this new phenomena comes in only when they are not able to access the service facility immediately. What they do, right? They can do differently, like either they can leave, right, without joining, or they can get into what we call is an orbit, right. This means that they are inside this orbit, and after some time, right, then they will make a call again. So, which we denote it as in this way. Okay. So, from here then they will re-arrive. So, customers re-arrive from orbit, right. That is what is this phenomena can happen. So, they can re-arrive here. So, this is primary customers and there is customers orbit who try to access the service. So, as such, you see here, because at whenever the service is occupied, a server is occupied, right. Since this happened, there is no queuing happens here. So, that is what you have to understand here, that there is no queue in front of service facility, right. That is what you need to look at. So, this is the general depiction. So, the main characteristics is what we are writing it here, what we just explained. An arriving customer enters the service immediately, enter into the service if the server is available. If all servers are busy, then the customer may either they leave the system completely, like the normal impatience or normal reneging kind of concept that you are looking at it, right, or temporarily leaves the service facility and return later to the service facility. Okay. While away, since he is going to come back to this service facility, the customers are said to be in orbit. So, this is the word that will be used in retrial queue to mean the customers who are not got access to the service yet, but they are waiting somewhere. It is not in front of the service facility, and unlike the other queuing system, they are waiting somewhere and they will make an attempt to gain into the get the service facility at a later point of time. Okay. So, those customers are what we generally termed as that they will be in orbit. Now, customers in orbit cannot see the status of the service facility, that you have to remember, because they will not know while in orbit whether the server is free in the middle, in between, before they make the retrial again. Say for example, when you are making the call to your car service center, you decide to try after 5 minutes, maybe the customer the service, the other side, the service agent got free in 30 seconds from the time you disconnected the call. So, but you do not know that, right, that is what it is the case. Okay. So, they will check only by re-arriving, as we saw here, they will check only by re-arriving from the orbit. So, arrival comes, they will go into the orbit, they will be staying there for some amount of time, then they will re-arrive to check the service facility, and they can check the status of the server only when they re-arrive it. Okay. And customers go back and forth from the orbit to the, so when next time also, like if they find is busy, then again they will take the same decision, right, the route is the same. So, they may go on indefinitely, or at some point of time they may leave due to impatience, or they can totally abandon the system. Anything is possible. When they are going back and forth from orbit, they will try until either the service is received or they abandon the system. Okay. Now, if you look at the orbit, right, the orbit is like a queue where the customers are there in that orbit. Okay. They wait for the service. In that sense, it is like a queue, but the difference is that they cannot see the status of the servers. It may so happen that, as we said, servers may be idle while there is a customer in the orbit. No concept of queuing order, because this is not an FCFS business in this case, and service in some sense you can think of it, is happening in a random order, because a customer may come, he may be waiting in orbit, but in between another customer might come, and that point of time the server may be idle, so he might get into the service immediately. So, there is no FCFS order also, and there may be 5 customers who will be waiting in the orbit, and depending upon who makes the next move of retrial, right. So, anyone might get access to the service. So, it is not that okay, again within orbit there is no FCFS or any order, it is random in this case. One limiting case that one can think is when the time spent in orbit for each customer is instantaneous, meaning the moment the customer sees that the service facility is busy, then he will get into the orbit, and as soon as he gets into the orbit, he will come back to the check immediately, which means that at each time point he keeps on checking to gain access, right. So, that is the case. So, in this case, like this orbit is like a queue, but again within the random service discipline. Okay, it is not again a first come first serve again, because any one of them can gain access to the server, though they each one is keep trying in at the instantaneous level, right. Now, as expected, like you have now some idea with different features when you are trying to add, the system becomes more complex, right. If you go to much generality, again the system becomes very complex, but except for a few simple models, right, the other queues are generally difficult. I mean difficult we say, but the difficulty level varies, and it is not that you cannot do anything with that system. No, it is not like that, but it becomes difficult. And for our course, when we are looking at how to incorporate such features into the queue, that is what our main aim is, right. So, but it's still quite a bit of easy in some sense for some few simple models, but it may not be so for more general systems that you might encounter in reality, and that you might want to consider it. So, you have to simplify it to a bit. Okay. So, what we will do is that we will take it up one particular model, which we call it as MM1 retrial queue. Okay. It is system behaves is in much like an MM1 queue in some sense, because the features of MM1 queue are there in a way that the customers arrive according to a Poisson process with rate lambda. There is a single server and the service times are exponentially distributed with rate mu. This is what is the MM1 part, of course with the assumption of independence between all those service times, arrival times and so on. Okay. Now, the retrial feature, any arriving customer upon finding the server is busy, that is a single server only. So, when he finds that the server is busy, enters the orbit and spent an exponential amount of time with parameter gamma in orbit before a retrial attempt. So, he spends an exponential amount of time with mean 1 by gamma. So, that is the average time that he spends in the orbit, which is exponentially distributed before he makes a retrial attempt. Okay. Now, we assume that the customers will retry until they are served, which means there is no impatience which we are not incorporating, right. If we incorporate, then this model becomes a bit more complex, and then that you can analyze. But for our simpler model, we say that every customer who has come to the system will leave the system only after getting the service. Until that time, he will be in orbit and he will keep trying to get the service. Now, all the inter-arrival times of this primary arrival, service times and orbit times, they are all independent. Now, this system can be described through the random variables or the processes in a way which we call it NST to denote the number of customers in service at time t, and since there is a single server here, so the number of customers in service could be either 0 or 1. So, this NST is basically either it will take 0 or 1 because single server. If you have multiple server, then accordingly 0, 1, 2, 3 and so on up to that server you will have this, that is a difference. NOT is the number of customers in orbit at any time t. So, this NOT could be any non-negative integer is what then you will get. Then this pair NS of t and NO of t is a 2-dimensional continuous time Markov chain with state space as I0, where I is either 0 or 1 depending upon whether there is 0 customer in the system with the server, or there is 1 customer with the server, Okay. So, or you could treat it as a server busy and server free in this single server case. N is the number of customers in the orbit, which could be either 0, 1, 2, 3 and so on. So, if you want to look at the total number of customers in the system, this will be the number of customers in the orbit plus the number of customers with the server, right. So, Ns plus No will give this N of t. So, this is the two dimensional CTMC which can describe the system state, but of course, we are looking at not in a time dependent fashion, but in equilibrium. So, in equilibrium you will have an equilibrium version of this two dimensional with this. Now, if you look at how does the state transition happens in this CTMC, we can look at this state diagram where you can see 1 denote the server busy, which is the first index. So, this row has the first index is 1, meaning that the server is busy serving a customer. 0 means this second row here is basically the first index represents that the server is free, that means there is 0 customer in the system, with the server there is 0 customer, okay. Not 0 customer in the system, but 0 customer with the server. Now, the columns represent the number of customers in orbit. So, N0 means that it could be like 0 customer in orbit. This is, these two represents 1 customer in the orbit. These two states represent 2 customers in orbit, but with either 1 customer with server or 0 customer with the server, but there are 2 customers in orbit. So, this is what is the depiction. So, this is number in service is what, either 1 or 0, number in orbit is 0, 1, 2 and so on. So, this is what is diagram. Okay. Now, if we denote as usual Pin to be the steady state probability of the system being in state In, then they satisfy the rate balance or flow balance equations, and the balance equation are given by this set, okay, where this is the equation, or this, the first equation corresponds to P0n state, which means for all these states, and the second equation corresponds to 1 1 onwards in the first line, and for 1 0 you have a separate equation, and for 0 0 you do not need separate equation because there is a n here which takes care of when n is 0. So, this term vanishes automatically. So, we can write it together. Now, let us look at what would have happened, suppose if it is the case. So, let us take a generic scenario here. For example, if it is state 1 2, what does that mean? There is one customer who is currently in service, right, and there are 2 in the orbit. Suppose if I pick this as my state, and then you can look at the balance equation in 1n, what would have happened here. Now, from here what would have been possible? The outgoing possibilities are that either there is an arrival comes. Now, whenever there is an arrival comes, since already there is one customer with the server, so the arrival will get into the orbit, right. So, it will move to 1 3 with a rate of lambda. Now, when it is in 1 2, if the service is getting completed for the customer who is currently getting service, then this so the system, the server will become free, but the number of customers in orbit would remain as 2. So, this will move to 0 2. So, with the service completion which is at the rate mu, this 1 2 from state 1 2 you will move to state 0 2, right. That is what you will have, right. So, this is what is the two things that can happen to go out from here, right. Lambda plus mu of P12 is what this term will be. Now, what about the right hand side? The flow into the state 1 2. What would have been there? It could have been 1 1, means server is busy serving one customer and there is 1 in orbit, but an arrival would have brought this to 1 2, right. That is this. So, that is this lambda, this one, okay. Or it would have been 0 2, means server was free and there were 2 customers in the orbit, and then an arrival happens. When an arrival happens, that arrival will directly get into the service. So, the system will become 1 2. So, that is lambda P0 in term. Or it could have been in state 0 3, right, 0, 3. Now, 3 customers in the orbit. Now, each one of them tries to gain access to the server retrial attempt, right. Since each one of them spends exponential amount of gamma, so the minimum is 3 times gamma. So, with the rate 3 gamma, from 0, 3, one of them can get into the service while other 2 would remain in orbit. So, from 0, 3 it can move to 1, 2, that is this term, right. So, this is this one and this case, right. Now, 1, 0, again there is only one possibility, this possibility is here, like this side remain the same, and here there is nothing like this can happen. So, that is what happens here, right. So, this is a special case with appropriate modification. Now, from 0 n what happens, like from for example 0 2 if I pick it, okay. From here it can come to here only via a service completion here, right. So, 1 2 to 0 2, right. But from here if there is an arrival, it will move to 1 2, or if one of them who are in the orbit currently with rate 2 gamma, if they could sense the the server becoming free, then like they will move to 1 1, right. So, with the rate this 0 2, from 0 2 it may become 1 1, right. That is the equation here. So, since this is same for all, so that is what is this equation. So, as you can see in a usual fashion, in our based upon our flow balance argument, the rate flow argument, in equilibrium, since the flow has to be equal across the state, right. So, we get this flow balance equations. Now, once we write down this flow balance equation, right, now it is up to us, like what you want to get out of this, whether you want to get a complete solution of P0n, P1n for all these states, or you want to get certain expected measures, that depends on the complexity. In this case, it is not that difficult to obtain P0n and P1n quantities. Okay. So, let us see how we can do this. So, we will take up again as usual, we will use the generating function approach to obtain the solution. So, let us define two partial generating functions, P0 of z, this is generating function for P0n, and P1 of z generating function for P1n, which means that we are writing this and this. Basically, what we are doing is we are compressing this whole line into a single entity, we are compressing this whole line into a single entity, right. That is what we are trying to do with the generating functions, right. So, that is what will give you P0 of P1z. Now, what one can do, this first equation which corresponds to P0n, so you multiply by z to the power n and you sum, right. When you do that, you will get this expression, which is essentially equal to this expression, which is equation 5 here that we are denoting it. So, this is just that the usual way that you multiply the equation by z to the power n and sum over all n, you will get this. Similarly, the corresponding equations of P1n, you sum over this quantity by z to the power n for n greater than or equal to n, and this one by z to the power 0, you sum these two equations, right, you will get this expression. Okay. So, now you see here the first one involves P0, and because there is a n here, obviously the derivative of that would give you that. So, there is P0 dash, the derivative of that, and then P1, whereas this is P1, P0 dash P1. Okay. So, what you can do from this expression, you can pick it up what is P1 of z, and you can substitute into the second expression, which is equation 6. Then what you will end up with, once you substitute P1 of z, right, here as well as here in these two, then you will end up with this equation where we denote rho as usual by lambda by mu. Okay. Lambda rho by gamma times 1 minus rho z times P naught of z would be P naught dash of z, because once you substitute for P1, then you have only two terms, P naught z and P naught dash of z. So, that would be of this form. Now, this differential equation is a separable differential equation, which you can write as P naught dash by P naught of z equal to this quantity, right. Now, you know that the solution of this is very simple, right. So, you can see that this implies that this is basically log of P0 of Z is equal to minus lambda by gamma, and this will be log of 1 minus rho Z plus some constant C1 is what then you will get, okay, right. That is what you will get, and from here you will get this expression where this is a constant. So, there is a constant times this quantity is what is your P dash P0 of Z, right. This is what you got the partial generative function corresponding to P0 ends. Now, you can plug this into this one, right. P0 of Z you got it. So, you find its derivative also, right. It is not so difficult because it is 1 over 1 by some function of Z. So, you can always find out its derivative. So, what you have is this one, right. P1 Z equal to rho P naught of Z plus gamma by mu Z times this. So, now P naught of Z, P naught dash of Z you can get from here, and substitute, you will arrive at this. Just one step you just substitute, then you will arrive at this expression. Okay. Now, in both we have this constant C, but the C can be found from the normalization condition. P naught of 1 plus P1 of 1 must be equal to 1 because total probability must be equal to 1, and that gives you C as this. So, now substituting here with this C, substituting here, you have now complete expressions for P0 of Z and P1 of Z. Now, so that is what these expressions are, right. So, this is what it is now. Now, you can expand it, okay, to a power series, and then you can get the coefficient. Now, rather than doing with here, we can get with here with C as a constant itself, which is very easy. So, what do you do? Like you look at the binomial formula, which is 1 plus Z to the power m, which is given by this, right. Now, there is one m factorial by n factorial times m minus n factorial. That n factorial you leave, and the remaining one, you can write it in as this product. This is assumed to be 1 when n is equal to 0. That is what we are assuming. This is the product, right. Now, take this expression, and then you can write it in this form, okay, expanding this one from this equation P naught of Z as a using this expression. If you expand, right, you will have this expression, right, and this is what you have here now as this expression for it, which again if you rewrite you will get something like this quantity times Z to the power n, and we know that this quantity where C is we already determined, right. So, this whole quantity is what our P0n, okay. Similarly, you can do it for P1n also because this is also of this similar form. Now, finally, we obtain P0n and P1n with as given in this expression for n. Okay. So, this is all for n greater than or equal to 0, n greater than or equal to 0. So, you will get as a complete expression here. Okay. In this particular case, it's not so difficult to obtain this expression, but as you would see, suppose if you introduce impatience here, then you will see that things become quite complex, even this one, but it is still doable. Okay. So, this is what it is in this simple MM1 retrial queue, the steady state system size probabilities. Now, once we have this in your hand, now you can answer questions related to the steady state performance measure. Say for example, you can look at the fraction of the time the server is busy, which you can obtain from here as this one as P1 1 of 1. So, you have expression for P1 of Z, in that if you put it you will get to rho, but you can also apply get this fraction of time server is busy as equal to rho using Little's law when you apply it to the server alone, and that will also be equal to the average number of customers in the service, right. So, this rho is actually also will be equal to the average number of customers in service, right, because P1 is what then you will get that from there. Now, if you want the PGF of the number of customers in orbit, right. So, then I have to add these two quantities multiplied by Z to the power n and then I have to get. So, that effectively means P0 of Z plus P1 of Z will give me the probability generating function for the number of customers in orbit. And if I denote LO to denote its mean number of customers in orbit, then LO I can obtain it as a derivative of this, which you can obtain it to be this, right. Now, if you look at this quantity, this is what you have to look at here. So, there is one term here and there is the another term here, right. So, this is typical of such retrial, and in many situations like this will also hold true, not just on retrial phenomena, but in somewhere else also we have seen already one or two, it may be true in any other case also. So, what we have, so this is a product of two terms, the average number in Q for an MMU in Q, right. This is average number not in system, but in Q in an MM1, and a term that depends on the retrial rate, right. So, there is this gamma comes into picture. Now, if gamma is large, okay, what does that mean? That the customer spends little time in orbit before making another attempt to gain access to the server, right. So, that is gamma large, meaning, right. And as in the limiting case, as gamma tends to infinity, that is what we are looking at, the instantaneously coming back with a retrial attempt to gain access to the server, right. So, they spend no time in orbit and hence are continuously able to monitor the status of the server. So, in such situation, as you can see, as gamma tends to infinity, this will be tending to 1. So, you will get only this term, which is basically what you would have had in the case of an MM1Q, right. This LO is the mean number of customers in orbit. Now that we have steady state probabilities are generating function, we can obtain all these quantities very nicely, there is no problem. Now, the mean time spent in orbit, suppose if I want again, okay. So, that is by Little's law is WO, which is equal to LO by lambda, which will be giving this. Again, you can write it as a product of these two terms. Similarly, the average time in system, right, and the average number of customers in the system, meaning everything included, right, can be determined similarly, where W is equal to W naught plus 1 by mu, because this is what is his waiting time and the service time for any customer, because we are not assuming that a customer leaves in between, right. They will be there forever in a way until they get the service. So, which you can obtain it to be this, and again you see here product of two terms, one correspond to MM1 and one with the parameter gamma, and L, which is the average number of customers in the system, again is a product of two terms, one corresponding to an MM1 and another term that is depends on gamma, and this could also be shown to be equal to LO plus rho, because we know LO is the average number of customers in orbit and rho is the average number of customers in service. So, sum of these two will be the average number of customers in the system. Okay. So, as we noticed, in all cases the service measures are the product of analogous measure for the MM1Q and a term that goes to 1 as gamma tends to infinity. Conversely, if gamma tends to 0, the expected service measures go to infinity because blocked customers spend an extremely long period of time in orbit before draining, right. That is what is the other extreme, gamma tends to 0. Now, to see how exactly this will be looking like, now we can just depict one, of course, we are not trying to draw in an exact manner, but just to gain the idea. Suppose if I look at this particular graph where gamma as in the x axis and say LO, which is easy to depict here. So, what the figure will look like is essentially it will be something like this, it will come, okay, and this would be the MM1 case and this is the MM1 retrial case, right. So, you can see here how it will behave, one can depict if you just plot it, whatever you have it L here. So, the corresponding MM1 case is essentially this and this. Again, it is intuitive that it should be like this, but again how exactly, whether it is coming like these or it is coming like these, right. So, you have to understand. So, for which you need to look at exactly the rate. So, for which you need the expression, that is what our expressions would help us to understand, right. So, this is lower value of gamma. For example, gamma here results in large number of customers in orbit, because each customer now wait long period before making a retrial attempt, whereas gamma tends to infinity. It is something like they are making at every instantaneous. In that case, it will be closer to your MM1 system. That is what you will give. Okay. And also like you would see that how this approaches and so on. This is simple one, but then if you have more parameters then of course you can have much more interesting phenomena which can be brought out from this. Okay. So, this is all about retrial. Of course, you have the steady state distribution, so you can talk about some more measures if you are interested. I mean, if there is anything, what is it, this many number beyond in the orbit and so on, suppose if it is the case. Okay. But at least the basic performance measure we can obtain in this manner. Okay. And these performance measures can be studied with respect to the retrial rate, not just retrial rate, even with respect to other parameters you can do, but since this is a new feature that we have introduced. So, how exactly this retrial rate plays out vis-a-vis without any such retrial phenomenon. Okay. So, this is another feature that can be added. Of course, here we have studied with respect to MM1 system, but of course, this can be extended to, for example, in the same particular case. So, you can say that you can add impatient feature. In that case, what will happen? Or you could have multi-server, right? Then how much is the complexity you can think, or any other generalization like in terms of the inter-arrival time distribution or service time distribution or any other feature. Like this one can study, and this is how the Markovian, the simple queues with MM1 for example, the moment you introduce retrial, you are no longer in some sense of a BDP model itself, it has become a more general Markovian model. In the same way, a BDP model, when you introduce more features, say for example, you could think of server failure, server being interrupted, the scheduling there could be, or server may not start work until certain number of customers in the system. Like this, there are n number of features that you can observe in reality, and in each of this case, right, the moment you want to incorporate into the feature, the simple Markovian model might become a more general, a bit more complex Markovian model, and any such model like what we have exhibited so far in this general Markovian system type, that you can in principle analyze, but how much, how far you can go, how much you will be able to handle depends on the scenario that you, as you have seen, for example, in the retrial case, getting the exact distributions even in a very simple situation is not that easy. In retrial, you could do that still, even if with a simple model retrial imposed on it. Like this, these things would vary, right. So, accordingly, like you have to base on that. So, this is what we see in the Markovian general setup. This is how one can incorporate the different features into the elementary models and see that how the system performs, and by incorporation of that, how much the system is being affected, in which way, everything can be studied in that feature. Okay. So, this is basically we are still within the Markovian framework incorporation of features. Of course, we have not incorporated all the features so far. There are plenty of other features which we will not be able to cover, but of course, that if you are interested, you can look deeper into this case. Okay. Fine. So, we end our discussion of this retrial to here. We will see in the next lecture. Thank you. Bye.